The next thing that we'll discuss is the concept of time ordering of events as seen by different observers in special relativity, and the connection between this time ordering and the concept of causality, that is, the idea that cause must precede effect. Now, as we've seen in special relativity, time is relative, that is, different inertial observers measure time differently. So it could be possible that events which have a particular ordering in time, for example, one event happens later than the other, could appear in a particular reference frame, could appear to have a different ordering where the first event occurs after the second event. Okay, so let's take a particular example and see how that works. So what I've drawn here is in a reference frame S, I've drawn the x-axis and the time axis, and I've taken an observer O and shown their future light cone as well as their past light cone. Now let's take a space-time point which lies in the future light cone. So let's take this point over here and let's call it the point space-time point P. And suppose we want to identify the time order of these events. So in our coordinate system, of course, O occurs at t0, which we've taken to be 0. And the event P occurs at a time which we will call Tp. And this is the labeling in the reference frame S. Now you can clearly see that the time of event P is greater than the time of event O. Since in this particular example, T0 is 0 and Tp is positive because it lies in the future light cone. So P occurs after O occurs in the reference frame S. So now the question is, if we go to a different reference frame, let's say S prime, and the time of event O is TO prime in that reference frame S prime, and the time of event P is TP prime. What we would like to know is TP prime greater than TO prime? That is, in another reference frame S prime, is it guaranteed that the event P occurs in the future of event O? Okay. So we don't know whether this is true. This is what we're going to try to find out. So let's construct the time axis for a different reference frame. Let's call that frame S prime. And let's suppose that the frame S prime is traveling with a speed parameter beta relative to the reference frame S. So we would draw a time axis. So let me just draw that here. And this we will label as CT prime. So this is the time axis of the observer S prime, and this axis makes an angle theta with respect to the time axis of the inertial frame S, where tan theta is equal to beta. Now you can clearly see that if I want to know in the frame S prime what the time is of event P, well, the first thing I would have to do is let me just draw the x prime axis. So here's the x prime axis. What I would have to do is draw a line parallel to the x prime axis, which passes through the point P in order to figure out the time at which the event P occurs. So let's draw that. So now you can see we've drawn this line which is parallel to the x prime axis and passes through the point P. And you can see where it intersects the t prime axis and read off how many units in t prime have passed. But the thing that you'll notice is that if we take the origins of t prime and t to coincide, that is t prime is 0 and t is 0 at O, then t prime is positive, okay, for the point P. So now we can clearly see that t prime P is, or the time of event P as measured in the frame S prime, and t prime O, which is the time of the event O as measured in the frame S prime, they preserve or they have the same time ordering. That is, the spacetime event P occurs after the event O, no matter which frame S prime we are in relative to S. So we have shown this for any point P lying in the future light cone of the point O. So all inertial observers agree on the time ordering of events within the future light cone. And therefore all inertial, so this region within the future light cone is also called the absolute future, because every single observer agrees that all points within this light cone are within the future of O. So this is called the absolute future region of the spacetime point O. And similarly, if you had taken a point P in the past light cone of O, all inertial observers would agree that the point P is in the absolute past of O. That is, every single inertial observer would agree that P happens before the event at O. So events within the past light cone are said to lie in the absolute past of O. Now, in fact, it's possible to find an inertial observer. It's always possible to find an inertial observer. So let's consider a frame S double prime. And we'll consider the frame S double prime such that the time axis of the frame S double prime passes through the point P. Okay, so in other words, what we're going to do is we're going to find a point, a frame S prime. Let me draw the time axis. So if I take my space-time point P again, I can now draw a time axis that passes through O and P. So that's shown over here. And there's some choice of angle, right, where this angle is less than 45 degrees. So that corresponds to a physical choice for beta. Okay, that is beta is less than 1. There's some beta less than 1 for which I can find a frame S prime whose time axis passes through the point P. And in such a frame S prime, the clock which is located at O is stationary, okay, and it also passes, that same stationary clock is passing through the spacetime point P. So now if we assume that in the frame S prime, this particular frame S prime, a time t prime has elapsed, or ct prime, since we're measuring time in c times t units. If a time ct prime has passed, we can calculate the spacetime interval between the point O and the point P. So spacetime interval between the points O and P. We could calculate this in any frame because it should be the same in every frame. But if we do the calculation in the frame S prime, what we would get is simply ct prime minus 0 square minus, since they're both at the same value of x, y, and z, okay, so minus 0 square. So in other words, this would be c square t prime square, which is positive, okay, since the events lie in the future light cone of O. And moreover, if I write this as c square tau square, what I see is that t prime is tau, or in other words, the time t prime that is measured on the clock in the frame S prime is a direct measure of the spacetime interval between the points O and P. Okay, So this time t prime is nothing but the proper time. It's the time measured on a clock at rest, which passes through the space-time points O and P. Okay, so t prime or tau is the proper time between the events O and P. And remember that I can use any other inertial observer to calculate the same space-time interval, okay? And they would also find the same value of the same space-time interval, or in other words, they would get the same quantity, c square times tau square. But if I want a physical interpretation of what tau is the time that has elapsed on a stationary clock which passes through the points O and P. So that proper time is, in the sense of being a space-time interval, is a Lorentz invariant quantity. All observers agree on the proper time that has elapsed between O and P, and they agree on the time ordering of events of O and P as well. Which is to say that for events in the future light cone, they would all agree that tau is positive. For events in the past light cone, they would all agree that tau is negative. Now let's talk about points which are outside of the light cone of O. So if this is the point O, let's consider a point P now, which is outside of the light cone of O. So let's consider this point P over here. Now this point is clearly separated from O in space as well as time, okay, according to an observer in a frame S. And now let's ask what observers in a different frame S prime would say. So we can draw the x prime and t prime axes for observers in a different frame S prime. So here I've drawn the x prime axis and the t prime axis. And if I want to find out what is the x prime coordinate of the point P, I could simply draw lines which are parallel to the t prime axis and x prime axis, and I would find that the point P is spatially separated from O and is temporally separated from O as well. However, it's possible to go to a frame, so let me draw a different frame now with a different set of axes. So here's another frame, okay, where this angle has become larger. That would correspond to a frame S double prime moving at a larger speed relative to the frame S. And in this frame, you can clearly see that the point P lies at the same instant of time, that is T double prime is also 0, okay, for the point P. So the point P occurs at the same time as the event O, okay, although it's spatially separated from O. So in frame S double prime, O and P occur simultaneously. Okay. Note that this cannot happen for events which are inside of the light cone. Okay, you can never find a frame in which those events occur simultaneously. But it can happen for events which are outside of the light cone. Another thing is, if you look at the ordering of events, the event O, let's say, occurs at a time 0 in the frame S, but the event P occurs in the future of this event O. Okay, so this is TP, which is in the future. However, in the frame S double prime, we've just seen that the event P will also occur at a time TP double prime, which is exactly equal to 0. Okay, so TP double prime would be would be 0. Okay, that is what we mean by the events being simultaneous in the frame S double prime. Now, something even more interesting is if I go to a frame, let's call it S triple prime, which is moving even faster than the frame S double prime is relative to S. And let me draw the axes X triple prime and T triple prime of this frame S triple prime. So I've shown here a frame which is moving with a much larger speed than either the frame S prime or the frame S double prime. You can see that by the angle made by this X triple prime axis being even larger than the angles made by the X double prime or X prime axis. And now in this frame, in the frame S triple prime, we can ask what is the time of event P? Okay, and what you see is that the time of event P, to find that, we would have to draw a line passing through P parallel through the CT double prime axis. So let's draw that. And let's also extend the CT triple prime axis. So here what I've done is I've drawn a line over here which is passing through the point P and is parallel to the X triple prime axis, and I see where this intersects the T triple prime axis. And you can see that it intersects the T triple prime axis at a time before O. Okay, so that is, if I ask about TP triple prime, in this case I would find TP triple prime is less than 0. Okay, so not only can you find a frame in which the events O and P are simultaneous, it is possible to find a frame. So in frame S triple prime, P occurs before O. Okay, so even though in frame S, P occurs after O, in frame S triple prime, P occurs before O. So that is, time ordering of events is not preserved when these space-time point or the space-time point P lies outside of the light cone of O. So in other words, we would say that space-like separated events or events which lie outside of each other's light cones do not necessarily have the same time ordering in different reference frames. Remember that events within the light cone, all observers will agree on whether they're in the future or in the past. But for events outside the light cone, different observers may disagree about whether these events, the time ordering of these events, or indeed whether these events are simultaneous or not. So now we can also find the space-time interval between the points O and P. So space-time interval between O and P. And it's easiest to do this in the frame S double prime, in which these events occur at the same time. Okay, in that frame, the event P occurs at the same time 0, but is spatially separated by, let's say, some amount sigma. Okay, or actually let's just denote it as delta x double prime. Okay, so in that frame, the times are coincident, so the time difference is 0 minus the spatial difference is delta x double prime square. So in this case, the space-time interval is negative, as you would expect for spatially separated events. And if we write it as minus sigma square, we see that sigma is equal to delta x double prime. So in other words, sigma, which is related to the spacetime interval between O and P, is just the proper length of a rod. It's the length of a rod placed between O and P, which is stationary in this frame S double prime. Okay, in which the events O and P occur simultaneously. So sigma is called proper length, and all observers agree about the value of this length, which is related to the space-time interval between O and P. But if we want an interpretation, a physical interpretation of what sigma is, we should go to the particular frame in which P occurs at the same time as event A, and imagine a rod placed with one end at O and one end at P. And sigma is the length of the rod as measured in that frame S double prime.